All right, hello everybody. Today we are going to be working on a problem that is a combined loading problem. So as you can see, there's multiple loads on this object, and we will be looking at this point of interest specifically and finding all of the principal stresses in it. So the first step when you see a problem like this is basically what you'd be given. You'd be given the object with the applied loads, the dimensions, and the size of the forces that are applied. And one thing to remember is that, or at least in this case for this problem, is they gave us the values as, basically the magnitude of the force, but we kind of want to know the direction that they're going in and stuff. So the force in the x direction here, it's actually following the x-axis, so that would be positive. But then the force in the y direction, it's actually going down as opposed to up here. So this would actually be a negative force. So negative 175. Here this is 100 pounds. And then here 125, that's also going opposite the z-axis, so we're also going to call that a negative 125 pound force. And what we want to do essentially is create a free body diagram, kind of like we would in statics, and use that to help us find all of the reactions and moments that are in this specific cross section here that our point of interest is on. So the way we do that is, well, we know that essentially, we know that this thing is in equilibrium, and we know it's fixed at that back end there. So what we're going to do is we're just going to basically chop this whole section off, and we're just going to work with this piece because we know that this isn't twisting or bending or moving. So whatever forces and moments are applied to this, there are reactions that are equal and opposite in this cross section right here. So we are going to draw this real quick, so I'll do my best to draw it nicely. So got that. You got an upward facing pipe here. We got another one that's sticking out to the side here. And then we have the cutoff point, we have H, our little point of interest. We have a 125 pound force here. We have a 100 pound force here. Hopefully you can see this, yep. And we have a downward 175 pound force here. And what we're going to do is we're going to, first we'll have in our axes just so we don't get confused at all. And we are going to write in essentially arbitrary representations of the reaction. So we're not entirely sure what their values are and what direction we're going in, but we know that technically there should be a reaction at x and a moment about that axis as well. We know that there should be a reaction in the y direction, whether it's 0 or not, and a moment about that axis. And then we know we'll do the same for the z, rz, and then a moment about z. z, my, mx. Sorry if it's a little messy. And then we have our dimensions here. So we know it's 12 inches here. Sorry, this isn't totally to scale. 6 inches here. And we have 10 inches there. And 8 inches there vertically. And now what we're gonna do is, we can pretty easily find what the reaction forces are based off these forces. But moments can be a little bit trickier because you need to analyze a lot about the plane. You know, this force, it would create a moment about the y-axis that twisted it like that, but then it's also elevated from the origin, so it actually also create a moment about the x-axis and stuff like that. So that gets kind of confusing. So what we want to do is we want to create this little sort of chart with all of our loads here. So px is 100, py is 175, and pz is 125. And so what we're going to do is we're going to make a chart with first essentially a position vector that goes from the origin to the base of said force. So for px, that said position vector would be 18 inches down the x-axis and 8 inches up the y-axis, and still in the same spot on the z-axis. So that ends you up with 18i, 8j, and 0k. And so that's going to be our position vector for this force right here. I'll separate these. And then we're also going to want to write the force itself as a vector. So that's pretty easy. We know that it's going in the x direction and it's going the same direction as the x-axis. So we end up with a positive 100i, 0j, 0k. And as we know, moment is a force times a distance, and if the distances are a little funky here with multiple axes, you can do the cross product of the position vector times the force vector, and that will actually give you the moment. And not only will it give you the moment, it will give you the moment as a vector, which means that you know exactly which direction it's going in. And you can add up the vectors of all of the moments from all of these loads, and that will help you find the total moment applied to this, which will allow you to find the reaction moments. So it's not too bad, it's just a little bit time consuming. So here this cross product comes out to 0i, 0j, negative 800k, right? So that means this moment, about the z here. And then we have 12i for 175, right? So 12 down, and 0j, and 10k, because it's over 10 inches here. Then we know that that is 0i, negative 175j, and 0k, because that's the force. 175 down the z-axis, or the y-axis, I'm sorry. And then the cross product of that gives you 1750i, 0j, and negative 2100k. And then for the last one, the position vector is the same thing, it's in the same spot, so 18i, 8j, 0k. But then obviously this force is, you know, not going in the same direction. It's going against the z-axis. So 0i, 0j, and negative 125k. And the cross product of that is negative 1000i, 225j, and 0k. So the total moment here that you get from all of these, by adding all of these up, you just add up the components here, you get moment equals 750, 225, or 2250, sorry, and negative 2900. And so that means that your moment about the x is 750 inch-pounds. Your moment about the y is 2,250 inch-pounds, and that z is negative 2,900 inch-pounds. So now we know all of our forces here, and we also know all of the moments applied to this. So we can find the reactions pretty easily because we know that this is in equilibrium. We know it's not moving, bending, twisting, you name it. So that means that the reaction in the x direction is going to be equal to the basically the negative of the force in the x direction. So that would be negative 100 pounds. Our y, our reaction in the y direction, again, same logic, it's the opposite of this, so negative 175 becomes 175 pounds. And our z becomes 125 pounds. And this is all nice and practical because, as you can see, all of these applied forces are only going in one specific direction. So we don't even need to find any sum or anything. We can basically just translate them straight over. And then for the moment reactions, it's going to be the opposite of this, so negative 750 for x, inch pounds, because it's a moment. My becomes negative 2250 inch pounds, again, a moment. And then mz becomes 2900 inch pounds. All right, so now we have all of our reactions, and what we're going to do next is we're going to individually analyze these reactions to find the different normal and shear stresses that are applied to the point of interest on all of these, because of all of these specific reactions. And then once we've done that, we'll be able to combine them, and well, that's where the name of these problems comes from. So the first one we're going to do is Rx right here. So that's a negative 100 pound force, and as you can see here, Rx is going along the x-axis, which is actually along the longitudinal axis of this pipe right here. So that means that this is an axial force. It's going along the main axis of this tube. And that also means that it's going to create a tension or a compression, because shear forces, they want to snap stuff like that. This is just going to want to stretch or compress this object. So we look at it as an axial force. So we say Rx axial. Let me make sure it's still in frame. Yep. All right. And with these, what we're going to do is we're going to kind of look at the cutoff point, and you can look at the angle, the plane that you look at when looking at the cutoff point is pretty important in these. But for the axial ones, you can basically look at it from either lateral direction. So I'm going to have mine looking like this right here. It's a nice little cutoff point. And we'll have our point of interest. And keep in mind, this is just for the purpose of understanding where everything is and what's going on. But it's sort of an arbitrary representation at the same time. You're just showing that you're looking at it. In this case, we are going to look at it in the z direction, so with the z-axis sticking out of the page, which means we will have the y-axis moving up like this, and we will have the x-axis moving up like that, x, right? Because you can see here the x goes out from this point. So this is kind of like flipped a little bit, but don't worry about that. And then there's our little point of interest, H. And so we know that these generally will create a tension, right? And they're not really going to create a shear force, so what we're going to do is we only really need to use the formula here for the most basic stress formula. Sorry for taking so long to get that out. So we have this 100-pound force here sticking out, and we know that it's going to apply to this and create some form of tension, right? Because the applied force is pulling this bar away from the wall. So it's pretty important to remember that this is actually going to create a tension, which means that even though our value here for Rx is technically negative, we are going to have our formula for stress here be negative P over A. And so that's because we know that this needs to end up being a positive value because we know that it is tension. So we're going to do negative 100 pounds over, and then A is the cross-sectional area of the object. So A is equal to pi times 1.5 over 2 squared. Because the thickness of this bar here is 1.5 inches. So, that's pi r squared, of course. And that results in us having a stress of 56.6 psi here. So hopefully you can see that. So now what we're going to do is we're going to apply this to some stress blocks to help sort of visualize all these stresses on this object. It's going to help us at the end. So we're going to draw our stress blocks here. There we go. There we go. So this is ZY plane, XZ plane, and the YX plane. That's still good, nice and visible. So these are our blocks here. And so because we know that this is a stress going in the X direction here, and it's positive, that means we're going to do outwards arrows on these along the X axis. So on both of these blocks, we'll have these outward arrows that show, tension, and the value will be 56.6 psi, which is our value for stress, of course. So now what we're going to do is we figured out all the stresses and stuff caused by Rx, and we're going to look at Ry. And Ry, as you can see, it's not like Rx. It's not axial. It doesn't follow this tube. It's perpendicular to it. So that's a transverse shear reaction, all right? Because it's creating a shear force. It's not going to be creating tension and compression. So we're not going to be worrying as much about, normal stress as much as the transverse shear stress. So for Ry, transverse shear, we can look at our little cross-section thing from, a lateral direction, much like this one, but unlike with this one, we need to make sure we're not looking at it from the direction that the force is acting in. So in this case, Ry is acting in the y direction, if that's visible there, acting in the y direction. So that means that we need to look at it on the xy plane from the z direction, right? With z coming out of the page. So we end up with basically the same little cross section as above here. So we basically end up with the same thing, right? We got h, and then got x, we got y, and then we also have our shear force, boom, 175 pounds, just going up along the y-axis right there. And the thing is with these shear forces, specifically these transverse shear forces right here that come from lateral forces specifically, you want to use the formula tau equals VQ over IT. And that is the shear force, right, times the first moment of area over the area moment of inertia times the thickness of the object. And now the first moment of area here, Q, is equal to y bar prime times a prime, right, like that. This value here is the area the outer area from our point of interest when you were looking at the cross section. So as if you cut it and you were basically looking at that face, but right here. When you're looking at that cross section, because you've got the X and the Y like this, right? You have H, your point of interest, right up top, H. This means that there's no outward area from H to that outermost fiber away from the neutral axis. There's none. So that means that A is going to be 0, which means that we know that tau will be 0 psi. So boom, we're done with Ry, just like that. Easy. But then Rz is also a transverse shear, but following the z-axis as opposed to the y-axis, which means that we need to look at it from the y direction. So with the y-axis sticking out of the page, and with the x and z-axis sitting here perpendicular. Sorry, I'm terrible at drawing. And that means that our point of interest, h, right here, because we're looking at it from the top, it's now sitting in the center there. That's h. And we have our positive 125-pound force, shear force, right here. So now we are going to be using the same logic, VQ over IT. But if you look at the cross section now, right here, if you look at the cross section with Y and Z, sorry, like that. Yeah, like that. Then you end up with a point of interest that's sitting nicely on the neutral axis. And that leaves you with a nice and big outer area, which means that you know that Q is not going to be 0 because the other value here is the distance from the point of interest to the centroid of said outer area. So if you know that those are both not going to be 0, then you know that you'll have a Q. And what you can do is you can just use this handy, much easier to perform formula to find Q on a pipe instead of doing what I just described. And you do 4r over 3 pi times pi r squared over 2, with r being the radius, right? So r is equal to 0.75 inches here. And what you get as a result of this formula is 0.281 inches cubed for Q. So now we have our shear force, and we also have our first moment of inertia. And what we want to find now is the area moment of inertia. So for a circle, the area moment of inertia is equal to pi over 4r to the 4th, which is equal to 0.249, right? So now we have our I value, so 0.249 inches to the 4th. And then T is just the thickness, so that would be 1.5, which is a given value. So now we can find tau, right? We do 125. Hopefully you're seeing this, yep. 125 times 0.281 divided by 0.249 times 1.5, and that equals 94.04 psi. And so now tau, you actually base the plane tau is on based off the dimensions of the point of interest. So here, h, it's basically like a tiny little flat circle, a little two-dimensional circle on this axis here, on this system of axes. And as you can see, because it's a two-dimensional circle, it has no y value. It just has an x value and a z value. So because of this little flat point of interest, we consider our tau, or shear stress, to be on the xz plane. So now what we want to do with this is we want to get it onto a stress block, much like this problem right here. So when we do that, what we're going to do is draw our usual stress block axes. Like this, boom, boom. Like that. Yep. And then we're going to draw our blocks on there. And now we know that it is on the xz plane. So it's not like a stress that follows an axis where there's multiple of that axis on the different planes. Here it's specific to a plane. So we're only going to draw tau on the xz plane. And we know that it is a positive 94.04 psi value. So the way to do a positive shear stress is to essentially have it be where the line that goes from the tips of where the arrows, the line that goes from where the tips of the arrows meet each other should have a positive slope. So in this case it does, so this is representing a positive shear stress, and it is 94.04 psi. All right, cool. So now we have done Rx, Ry, and Rz, and we're going to be moving on to the moments. So first we're going to start with mx, moment about the x-axis. And if you look, the moment about the x-axis, it's as if you grabbed this bar with your hand like this and you tried twisting it. So that's called torsion. So it's as if you were to grab the top and bottom of a soda can with your hands, and you were to turn one hand clockwise and the other hand counterclockwise. You're applying torsion. So mx here, it's not going to try and bend it this way or this way. It's just going to try and twist the object. So because of that, we consider mx to be torsion. And with torsion, specifically, we know that it's not going to be creating any tension or compression because it's not, pushing or pulling anything in and out. It's just twisting. So it's going to create a shear force. And the way that we want to look at it, because we're going to make another sort of cross section, is we're actually going to be looking at it from the direction that the moment of torsion is acting about. So we're going to have the x-axis actually coming out of the page, and we're going to be looking at it from a sort of front cross section. So it's going to be a circle, of course, and here are the y and z axes, of course, right here. Okay, and then we have our point of interest there, h, right? So if you look at this, kind of should make a little bit of sense. And what we know is that for torsion, the equation we use is tau equals T rho over J. So T is the torque applied here, the applied torque. And then rho is the distance from the center here to the point of interest, essentially. So for us, it'll be the radius. And then J is the polar moment of inertia. It's very similar to the area moment of inertia, but not entirely. And it is, or actually might be entirely similar. And that is defined by pi over 2 times p to the fourth, which if you were to simplify 2t times rho over pi over 2 rho to the fourth, you end up with, sorry for taking so long to get that out, 2t over pi rho cubed. All right. So this is the formula we are going to be using. And we know that our applied torque, or our moment reaction, which is effectively the torque in this case, we know that it is negative 750, and negative torques and moments means clockwise, so it's going to do this, 750 like that, inch-pounds. And here, we're basically just going to have a pretty straightforward thing. We're just going to plug it in. So here we're going to end up with 2 times negative 750 inch-pounds divided by pi times, and 1.5 inches over 2 would be that distance we're looking for, so 0.75. 0.75 cubed. And so there we get negative 1131.8 psi right here. So that is the shear stress that we have found as a result of this moment reaction. So now we are, as usual, going to draw our stress blocks to help us understand a little bit more what's going on. So Z, X, Z, Y, like that. Finish up these blocks here. But now this is negative, so we're going to do the opposite of this, essentially. So down, to the left, up, to the right. And that value is negative 1131.8 psi. All right, so that is good. So now we have done mx, and we just have 2 more left to do. So for moment about y, if you look at it, the moment going about the y-axis, it would try and sort of snap this, sort of like you would snap a branch off of a tree. So that's called bending, right? It's not twisting, it's not creating any torsion, it's just bending. And the thing about bending is that it's not going to create a shear force, it's actually going to create tension and compression. Because if you think about it, when you bend a cylinder, the top of it is actually stretching and getting longer, and the bottom of it is actually compressing. So you end up with tension and compression as a result of bending forces. So for bending, the way that you want to analyze it is you actually just look at it from the direction of the axis that the moment is acting about, much like torsion. So here you would draw your little cross section as usual. Have our draw a little z-axis or something here, and x, and we'll have h like that, and we'll be doing pretty good. Yeah, so that's about right. And then we obviously, want to draw in the that bending moment, right? Because it's trying to bend it like that. So that bending moment that we draw in, that is 2250. So actually, I'll have it face the other direction because it's negative, and negative means clockwise in terms of bending and moment and all that. So the thing about this, though, is that for bending moment, we're actually, it creates tension compression, it doesn't create shear. And the formula we use for it is actually my bar over I. So m is that, that a moment that we know of, 2250 here. And I, as we also know, is just the area moment of inertia. And then y bar is the perpendicular distance from the point of interest to the neutral axis. So if you notice here, on this object, the neutral axis, of course, because it's symmetrical, it's going right down the middle, and that's exactly where h is. So because of that, we know that y bar is equal to 0, which means that we know that this is actually not going to be creating any stresses. So the stress here will be 0. So now that we have that, we know a moment about y, so we know that we have our stress going in the x direction from that tension and compression force there. We know that we have our shear force here on the xz plane that comes from this transverse shear. And now we're going to move on to the final reaction, which is yet another bending reaction. Make sure this is in frame. So for the moment reaction about z, it's another bending one. So we're going to follow the same rule of we're going to have the z-axis sticking out of the page because it is acting about the z-axis. So that's x and that's y. And here we know it's 2900, so counterclockwise positive, 2900 inch-pounds, like that, right? And we know that the distance of our point of interest, which is up here because of this plane that we're looking at it from, is 0.75 inches away from that neutral axis right there, because this thickness overall is 1.5 inches. So that means that our y bar is equal to 0.75 inches. We know our moment is 2900 inch-pounds. And we know that I is pi over 4 r to the 4th, which is equal to pi over 4 times 0.75 to the 4th, so 0.249 inches to the 4th, which is something we saw earlier. So now that we have all that, we can find our stress. So again, this is a stress that would be going in the x direction, because if you look, it would be bending this either down or up, which being that this is actually being that this is actually on one of the outer fibers here, it's going to be experiencing a very large amount of tension or compression, and it's going to be in that x direction because it's either going to be pushing it, smushing it in like that, or pulling it out like that along that x-axis. So we know that this is a stress in the x as well, and we know that it is equal to 2900 inch-pounds times 0.75 inches divided by 0.249 inches to the 4th, right? And that gets us 8734.9 psi. All right, so now we have our stress in the x direction here, 8734. So we're going to create our final, or actually our second to last set of stress blocks here. So y, z, z, x, y, x, and make sure it's still visible. Okay, do that, do that, do that. And we know that this goes along the x direction and it's a positive value, so we're gonna have our little tension here. All right, and then, so that is 8734.9 psi. So now, if you look at everything here, we're going to do the combined part of the combined loading problem. We're actually going to draw another set of stress blocks here, but this time we are going to include everything. All right, so we know that we have 8734 psi as well as 56.6 psi, all acting in the x direction, all in tension. So that leads us to having a total value by adding them together of 8790.6 psi. Right? And then if you look at the shear stresses that we have, here we have negative 1131 psi, and here we have negative 1131 psi, and then there we have 94.04 psi positive. So that comes out to a total of negative 1037.8 psi, which will we be putting here. Negative 1037.8 psi right there. And that is our shear stress. So now we have essentially a sigma x, which is 8790.6 psi. We have a sigma y, which is equal to 0 psi, right? Because there's no y, sigma. And then we have our tau xz, which is equal to negative 1037.8 psi. So now that we have this, what we can do is we can essentially just use the formula from Moore's circle that we worked on in our previous presentation to find the principal stresses and max shear stress. So this formula is sigma x plus sigma y over 2 plus or minus, it's kind of like the quadratic formula. Actually, no, it's not. I don't know why I said that. Ignore that. And then sigma x minus sigma y over 2 squared plus tau xz squared. So if we plug everything in, we end up with 8790.6 plus 0 over 2 plus or minus square root of 8790.6 over 2 squared plus negative 1037.8 squared, like that. So then you end up with sigma 1 and sigma 2 values that are 8,958.3 psi and negative 120.9 psi. And for the tau max, it's actually quite simple. It's just this portion of the formula right here. So that part right there sigma x minus sigma y over 2 squared plus tau xz squared, square rooted, gives you tau max equals 4516 psi. And those are your final answers. So, just to recap, okay? We had our starting problem here, and we were given some loads that are placed on it and a point of interest. What we did was we went and we found, or made ourselves a free body diagram here, and we drew in our reactions that we know we have, and we figured out what those reactions are using this sort of little chart method with vectors. Let's check these guys off. Now that we've done that, we then went ahead and we individually analyzed all of the reactions that we found. So Rx, we knew that it was in the axial direction because of the way it went along the x-axis. And we knew that it was going to be tension, so we did negative P over A. And this is what we got. So we added that to our stress blocks. Then we looked at the transverse shear forces that are applied to this, these ones that are perpendicular to the length of the tube. For those, we had to use VQ over IT. But for Ry, we knew that H was in fact at the very top of the cross-section, which means that there is no outer area for H, and there is no Y as a result either. So we knew that tau was 0 as a result of that. But for RZ, we did not know that, so we knew, and in fact, we knew that Q would have a value, so we used this handy formula for Q to find it, and then we plugged everything in to tau, and that's how we found our value for tau here. This is also a tau xz value. We know that because of the dimensions of the point of interest. It is sitting flat on the xz plane. So we got that tau xz value from RZ, and we moved on to the moment reactions. And because the moment about the x-axis is going to twist, right? It's going to twist like that, as opposed to bend like that, we know that it's not going to create any force of tension or compression. It's going to create a shear force. So we use this formula, torque times rho over polar moment of inertia, and that's how we found this value here. And as you can see, it is also on the xz plane, but it is negative. That is because we got a negative value. Now, in the moment about y, this we knew to be bending, because it is not going to twist, it is going to bend. But what we also knew is that you need the formula moment times the distance from the point of interest to the neutral axis over area moment of inertia. And because the point of interest was on the neutral axis, we knew that distance was 0, so we got 0. All right, so now we found everything except for that final moment reaction, which was a bending moment. And we had it going, there we go, much better. We had it bending like this, and we knew that there was in fact a solid y value because y was up and away from the neutral axis. So we were able to calculate it using the previously mentioned formula, and we found 8734, and we knew it was acting in the x direction because of the way that the pipe would bend like this. It would create a torsion going along the x direction, or a tension, not a torsion, or a compression, potentially. But here it says tension, so we'll call tension. And then now what we did is we took all of that stuff that we found, and we said, okay, we're going to add it all together, all those stress blocks, we're going to all put them on one set of stress blocks, and we're going to use that as our sigma x, sigma y, and our tau, in this case tau xz, for our formulas for Moore's circle, which will then allow us to find the principal stresses. Thank you for listening.